Well, hello and welcome YouTube. Mr. Robins back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside as we jump into section 4. It's the 4.1 to 4.3 quiz review in the textbook, and it's got 20 questions in total. I don't know if they're in order or not. Sometimes they shuffled up a little bit. Some graphing to be had. You got to use the graphing calculator, I'm sure, as well. So get ready. Let's go ahead and just get started on it. We're going to start with numbers 1 and 2, where we find the indicated real nth roots of a. This is out of section 4.1. When they're talking about roots, you're thinking about when you solve for it or when you graph it, where they actually cross axes. So this like plus or minus stuff kind of matters here. The nth root is the fourth root, so we are taking the fourth. Let's see, I forget how we wrote this as a whole. I did this a couple sections ago. So like the fourth root of 81, but the thing is we have to consider the positive and negative versions of this, because when we raise them to the fourth power they would turn positive. Now the fourth root of 81 is 3, but of course because negative 3 to the fourth power is also 81, it's plus or minus 3. There are two answers to it. Number 2 is the fifth root of this negative number. Now, just as a quiz review, I want to make mention, since this is the only other question like this, I suppose, you can't take the even root of a negative number. That would just be no real roots. But there's a real odd root. There's a real root to taking the odd root of a negative number. So if we take the fifth root of negative 1024, it's the same thing as the opposite of the fifth root of 1024, just to kind of get things going. I think the number's 4, or negative 4 in this case, and that answer is negative 4 here, because negative 4 to the fifth is negative 1024. And that's the idea of that, and that's how they kind of compare. Odd roots would only have one answer, either positive or negative or 0, based on whether the number is positive, negative, or 0. Even roots would either have 2 real roots if positive, 1 real root if 0, and no real roots if negative. All right, number 3, part of the same section, evaluate 16 to the 3/4, part A, and 125 to the 2/3 power, part B, without using a calculator. Explain your reasoning. So part A, we have to find out 16 to the 3/4 power. This answer is not 12, and it's not 16 3/4. You're not multiplying or dividing by it, you're raising to the power. Now, raising to the power is equivalent to taking the fourth root of 16 and then cubing that result. You could cube 16 first, get a massive number, and take the fourth root, and you're messing yourself up in the process if you do that. The fourth root of 16 is 2, and 2 cubed is 8. My explanation is my calculation. The conversion from rational exponent form to radical form, though, is right there. The denominator of the exponent becomes the index of your root. Part B, we have 125 to the 2/3 power. No doubt we're going to be doing the same thing on this problem as we did on the previous one. So we'll take the cube root of 125, and then we will square that result. Okay, so the cube root of 125 is 5, and 5 squared is 25. So no calculator, those are the correct answers. Again, it's not 2/3 of 125 or 125 and 2/3. Numbers 4 and 5, also section 4.1, we got to find the real solution or solutions of the equation. Round your answer to 2 decimal places when appropriate. So we'll go to the calculator if we have to, if something's not a perfect square or something like that. So number 4, we have 2x to the 6th power equals 1458. We will divide both sides by 2 to get the x to the 6th by itself, and that is 700, I don't know why I don't know, 729. And then we take the 6th root of both sides. Now let's say you didn't know this 6th power value. You could go to the calculator and type it in, but maybe you're like, I don't even know how to type 6 root in my calculator. There's a way to do it. But you could also do 729 to the 1/6 power. Now that's just an in-between that I'm writing for you in case you want to go to calculator mode. But 729, I believe the 6th root of that is 3. And in these cases here, plus or minus. And in these cases here, we are considering both solutions if it's an even root like that. So I should even be putting plus or minus there as well, as far as calculator goes. But plus or minus 3. 3 to the 6th is 729. Negative 3 to the 6th is 729. All right, number 5. X plus 6 to the 3rd power equals 28. This one is, well, take the cube root of both sides to begin with. There's no plus or minus for odd roots. 28 is not a perfect cube. 27 is, but 28 isn't. So x plus 6 equals the cube root of 28, and we have to subtract 6 from both sides to solve for this. X is negative 6 plus the cube root of 28. Oh, how much my hand wants to do plus or minus on that. It's like thinking about doing it there. So I'm going to go to the calculator for this one to actually get the approximation. And we are going to get, I don't know. This is from a previous section I had to do. So I actually got to clear all that out. Let me reset my calculator. This was from section 4.3. I'm recording this video right after. Memory, reset, all RAM. Okay, so here, because I want to reset all my windows as well, I can do negative 6 plus. I have a cube root option here, option 4 under math, and I can type 28 like that. You could also do negative 6 plus 28 to the 1/3 power, and if you do 1/3, make sure you put it in parentheses like that, and you should get the same answer there. So we're going to get around negative 2.96, negative 2.96. They said 2 decimal places. And that'll be it. Okay, we're going to section 4.2 on numbers 6 through 10, but on 6 through 9, they ask you to simplify these expressions that don't have variables. So on number 6, we have 48 to the 1/4 power over 6 to the 1/4 power, all raised to the 6th power. Now I have several options on what I can do here. One of the properties we can do is we can apply this exponent to both the top and bottom of this. So if I write this option in blue, we can make this become 48 to the 1/4 power to the 6th, divided by 6 to the 1/4 power to the 6th, which now these exponents will multiply together. This is 48 to the 1/4 times 6 over 6 to the 1/4 times 6. And I'm writing all these because I don't know what kinds of things we're going to see again. So I want to show you every which way you can do this. Now that's 48 to the 6/4. 6/4 reduces to 3/2. We got 48 to the 3/2 power on top and 6 to the 3/2 power on bottom. Now, because they both share the 3/2 exponent, we can rewrite that as 48 over 6 to the 3/2 power, which is 8 to the 3/2 power. And 8 to the 3/2 power, that could be a final answer. That could be one of the things that they just write as it. If I did it a different way, it would be, oh gosh, it would be the square root of 8 cubed. And the oh gosh thing about this is this would be 2 root 2 cubed, which means now you have to do 2 cubed times root 2 cubed. I don't know if this is a way to go about a final answer, which is 8 times, see, root 2 cubed is root 2 times root 2 times root 2, which is root 2 times root 2 is 2, and there's a root 2 there, so this is 8 times 2 root 2, which is 16 root 2. So this could be an answer here, 16 root 2, or this one, either is fine. Now, I'm sure this is fine as far as simplifying goes. They're acting more like just use the numbers to get it down to a single value like that. Otherwise, this should be equivalent to that, 16 root 2. Sure. Now, another way we could do the same problem, I'll do it in green. That's 48 to the 1/4 over 6 to the 1/4. This is probably the easier way to do it next. But you have to recognize what it is you have to do to begin with. Is because they both share the same exponent, now we could begin with the 48 over 6 to the 1/4 power as a whole, and that's still raised to the 6th power. Now the 6 and 1/4 can multiply here as, I'll do the rest in green, 48 over 6 is 8, and 6 times 1/4 is 3/2. So you still get to the 8 to the 3/2 from there. It looks like less steps because I could do multiple things at once. It depends, but you still get to that answer as 8 to the 3/2 power. And like I said, that's probably the good accepted one. 16 root 2 should be the same value though, as a final answer. Okay, let's jump to number 7. On number 7, we have cube root or 4th root of 3 times the 4th root of 432. The only reason I pause is because, listen, there are two, multiple ways to do this one as well. Let me do that. You could multiply these two and get them under one thing, right? You can do 3 times 432, give them under 1. And that would be the 4th root of 1296. Now, assuming we didn't have a calculator, would you know if this was a perfect 4th power value or not? I believe it's 6. 6 squared is 36, 6 cubed is 216, times another 6 is 1296. So this actually ends up being 6. That's one way to do it, but going bigger doesn't always work. Number one, you don't always know what it simplifies to. Number two, if it doesn't simplify to something like that, you're going to have to do extra work to actually break that down to perfect fourth power values. Now, 3 is not a perfect fourth power value, but there should be a smaller one within 432 that we can do. It's still a bigger number, so I don't actually know what it is. You know, we could break it down in some certain ways. If you divide it by 2, well, you get 216 if you divide it by... Oh, that's not a perfect fourth power value, though. Fourth power values are, 2 to the fourth is 16, 3 to the fourth is 81, 4 to the fourth is 256. This is already more than half of 256, so that won't work. 81 times 5 is 405. That doesn't work. 16. Can I divide by 16? We can do a couple 80s. 16 times 5 is 80. Times 5, 25. Yeah, I think 27. So you can do 16 and 27. So this might not be any easier. So we got 3 and 4th root of 16 and 4th root of 27, like that. 16, 4th root of 16 is 2. Now, these themselves aren't perfect fourth power values, but if you combine them, because that's generally the goal, right? When you simplify, you got to bring them back as 1. 3 times 27 is 81, and the 4th root of 81 is 3. So you get 2 times 3, which is 6. So there's a lot more to do with that one, I suppose. I don't know which one works better for you. That one works better for me, but that's because I know what those numbers are. Okay, number 8. Number 8. You have 1 over 3 plus root 2. And we have to simplify. Now, the simplification here is not turn this number rational, but it's turn the denominator rational. We have to rationalize the denominator by multiplying by its conjugate. 3 minus root 2 over 3 minus root 2. Now, when you do this, you create a difference of 2 squares. This turns into a squared minus b squared. And 3 squared is 9. And root 2 squared is 2, you get 9 minus 2. 1 times these two things is just 3 minus root 2, not much. And 9 minus 2 is 7. So you get 3 minus root 2 all divided by 7. This is an example of simplifying that one. You've rationalized the denominator. The top is irrational, whatever. It's equivalent to this answer, but it's now rationalized. That's what we do with it. On number 19, we have cube root of 16 minus 5 times the cube root of 2. Now, in this one here, your goal is to combine like radicals. I just say like terms in this scenario. They are not alike currently. There's nothing you can combine as it stands, unless I could maybe turn cube root of 16 into something root 2. That's generally the goal. Cube root of 16, 8 is a perfect cube, so we can split this up in cube root of 8 times cube root of 2. And the cube root of 8 is 2. So we get 2 root times the cube root of 2 minus 5 times the cube root of 2. And I always say this is like 2x minus 5x. You subtract the coefficients, right? And it becomes negative 3x, or negative 3 times the cube root of 2. And that's the simplified result of number 9. Now, number 10 asks you to simplify this thing with variables. Some things of note. Well, the main thing of note here is that it does not assume all variables are positive. You see the problems down below, it says assume all variables are positive. This one does not say that, which means there may be some absolute values involved. And if there are, I'll be sure to explain them. The other thing is we don't take the 8th root of these numbers. We divide these by 8 because taking the 8th root of something also means raising them to the 1/8 power. So if I want to give you a visual representation of what we're about to do here, this means x to the 9th, y to the 8th, z to the 16th to the 1/8 power. And as you know, a couple things. Number 1, this can go into all 3 exponents. And number 2, a power to a power means you end up multiplying those. So 9 times 1/8 is 9/8. That means you divide 9 by 8, you divide 8 by 8, and you divide 16 by 8. Now, I normally don't write these in between steps. I just go straight from here to here saying I divide 9 by 8, etc., etc. Now, let me actually start with z. 16 divided by 8 is 2. You're actually left with z squared. It's no longer inside the square root anymore. Now let's go to y. 8 divided by 8 is 1, so you're left with a y on the outside. The difference, though, is that any negative number raised to an even power would turn positive. Now that this y is raised to the first power, a negative number raised to the first power would stay negative. So when it comes to simplifying and we want these to be equivalent to each other, we want to make sure those y's stay positive even when raised to the first power. So we have to take the absolute value of y with that. Now x is an interesting one here because 9 can't divide by 8 perfectly. 8 can go into 9 once. So an entire x can come out of here, just like the y and the z squared. But one remainder of x, it stays inside of that 8th root radical here because it never came out. This would actually be the final answer of this thing here. This would be the final answer of this. So when you divide, your quotient comes on the outside, meaning 9 divided by 8 is 1. With a remainder of 1, the remainder stays on the inside there. Now you might be wondering why. Oh, x, by the way, needs... x doesn't need an absolute value because the x on the inside is all good. Actually, let me think about that because now if x is negative, x can't be negative to begin with. I guess that's a part of the redundancy or therefore. But anyway, what was I going to state here? Z doesn't need an absolute value because squaring it would still turn it positive, just like when raised to the 16th power. So we all good there. All right. Numbers 11 through 13, this time we assume the variables are positive. All right. So on number 11, we have the cube root of 216 p to the 9th. The cube root of 216 is 6. And the cube root of p to the 9th, you divide the 9 divided by 3, as you just kind of saw before. So this is going to be p cubed. It's 6p cubed. That's it. Number 12. These problems got weird and tough in the actual section. This is section 4.2. They got tough and weird in that section on some of them. They were like some of the hardest ones I've ever even had to do before, as far as like rationalizing. Speaking of rationalizing, this might be one of those. 5th root of 32 over 5th root of m cubed. The 5th root of 32 is 2. I'm going to leave that like that. 5th root of m cubed, can't do much with it as it stands. I need to rationalize the denominator. That doesn't mean I just multiply top and bottom by this number exactly. I just want to multiply it by enough so that I get a perfect 5th power value. A perfect 5th power value would be m to the 5th. So let's multiply m cubed with m squared. But this needs to be in a 5th root as well for them to actually properly multiply. So on top and bottom, we're going to multiply by the m squared. Now, so on bottom, guys, we're going to have, right, the 5th root of m to the 5th. Those will cancel. You'll be left with m on bottom. On top, you have 2 times the 5th root of m squared. And on bottom, we have that m. That's simplified. It might look worse to you than that, but it is simplified. We have a rational denominator on number 12. Unless m, of course, is an irrational value, but we don't have any control of that. Number 13. Number 13, we have the 4th root of n to the 4th times q plus 7 times n times the 4th root of q. Once again, this is all going to be about kind of combining like terms. Even if you consider n, even though it's on the outside, you can almost consider it like a variable within. I want these to be the same, and they're not the same. And I want to then add the coefficients afterward. So to make these the same, I'm really looking at this one. I have the 4th root of n to the 4th. Now the 4th root of n to the 4th is n. So this is n times the 4th root of q. And this is plus the 7n times the 4th root of q, like that. Now they're the same, right? These are like terms right here and here. What's the coefficient here? It's a 1. So I'm going to do 1 plus 7, and I'm going to get 8. This becomes 8n times the 4th root of q. 8 times n times the 4th root of q. That would be your final result. You might say, wait, I thought the 4th root of n to the 4th was the absolute value of n. Don't you need that? And then they wouldn't be alike? Remember, we're assuming all variables are positive for this set here, so we don't need absolute values for things. Number 14, totally different section, totally different set. This is section 4.3. Graph f of x equals 2 times the cube root of x plus 1. Identify the domain and range of the function. So f of x equals 2 times the cube root of x plus 1. This is where we are graphing radical functions. I do these without a table. I will attach this graph paper for you. I'm going to use this, and I'm going to rotate it on over. So you might have to use a rotated version of this graph paper here. Now, the original parent function for cube root of x has 0. The cube root of 0 is 0, and the cube root of 1 is 1, and the cube root of 8 is 2, and things like that. This is not the function, by the way. Cube root of -1 is -1. Cube root of -8 is -2. You have a snake-like appearance of this graph. We have the same snake-like appearance, except we're vertically stretching by a factor of 2, and we're translating up 1 unit. So I'm going to start with the translation up 1 unit, graph everything in relation to this. Instead of going over 1 up 1, I'm going to go over 1 up 2. The cube root of 1 is 1 times 2 is 2. The next perfect cube is 8, and the cube root of 8 is 2. Double that, you get 4. So that's me going to the right. Going to the left, because we can take cube roots of negatives, we go left 1 down 2, and left 8 down 4. 2, 4, like that. And this will be the example, or this will be our thing right here that we can go ahead and graph. And it's kind of a squiggly thing. Now, we can't fit the next set of points over, because what we would have to do for that one is go 27 over, because 27 is the next perfect cube for 3. So I can't fit that. This graph only goes over 17 units, left, right, etc. Give me 1 sec. I have to send something out to people. Hold on. Okay, sorry about that. Okay, so there should be the graph of that one. Identify domain and range. Now, regarding this, the domain is all real numbers. The range is all real numbers. Now, I don't know if we're going to graph a square root function later. I mean, there are some down here, but they don't say domain and range. The domains for square root functions are limited, right? It doesn't go forever left. It doesn't go forever down, because we can't take square roots of negatives and get negatives out. So those are limited. Cube root functions can go forever left, right, up, and down. All right, numbers 15 through 17, we are going to describe the transformation of the graph of f, represented by the graph of g, then write the rule for g. Let me take a higher quality version of these ones where I can copy and paste. I'll even get the actual equation in my copy paste. So number 15, I copied and I'm pasting this big guy right here. Okay, what did they want? They wanted the transformation, describe the transformation, and then write a rule. So this one, we're taking our original square root function, which would have started here, like this, and it looks like it just translated 1 unit to the left. We're taking this, we're saying, hey, move it over here. See, look at that, perfect. So a square root function is over 1 up 1 over 4 up 2, right? Square root values. So the graph of g is a translation 2 units or 1 unit left of the graph of f. That's it. Now, as far as the equation goes, this is that. So, you know, g of x, I mean, if I did one more step, these are kinds of problems that we had to do before. This is f of x plus 1. So we substitute x plus 1 in for x, and we're going to get g of x equals the square root of x plus 1. You can see f of x is the square root of x. This is the square root of x plus 1. It's like its vertex form, and that would be its appearance there. All right, number 16. Number 16 has at least 2 things going on that I can tell. Let me get the high quality graph here. I'll even get the 16 involved in the copy job, so I don't even have to write that. One less thing to write. Isn't that fun? But I have to shrink it down to size, of course. All right, there's my number 16. That looks a little weird. Maybe I should write the 16 for myself next time. Okay, so for number 16, a cube root graph, we just saw before that it has this over 1 up 1 over 8 up 2 kind of thing, and it would squiggle this way. Well, this one does, that's a bad drawing, but this one does 2 things. It's moved up. You can kind of see that new center, and then it's flipped over, right? And then it's flipped over like that. Now, is it going over 1 up 1? Yes, but so there are 2 things going on. There's a reflection. You can argue one of 2 forms of reflection, because an odd function, this is an odd function, a cube root function can flip over the x-axis or the y-axis and be the exact same graph. So this description could have one of 2 things. I'm going to talk about flipping over the x-axis. I know it looks like a flip left and right. It's also flip up and down. So the graph of g is a reflection in the x-axis. Now, I'll say, if you said y-axis, you would still be right. In the x-axis of f, followed by a translation 1 unit up. Again, if you said y-axis, you would still be right. That's not true for square root functions. That is true for cube root functions. Now, as far as my answer goes, I would be putting negative cube root of x like that, and then plus 1 to go 1 unit up. If you did a reflection in the y-axis, I guess technically you'd be writing it like this, cube root of negative x plus 1, and that is still fine. You can also factor that negative 1 out and then take its cube root and get the negative 1 that I have. That is completely acceptable. I'm going to work in that one. I prefer that. Number 17 looks like more translation stuff and no more differences on stretches and all that. So, okay. So let's check it out on number 17. This time I feel like I want to write it. That wasn't so hard to write. All right, f of x equals square root of x. Yeah, you know, again, square root function would have started just right here and gone through. So what are we doing? We're going 1 unit right and 2 units down right there. And then it's the same graph. There's no stretches, no reflections, no changes there. So the graph of g, not much of a quiz question. The graph, not compared to the other one, of g is a translation 1 unit right and 2 units down from f. So this one, 1 unit right, we'll have to put the x minus 1 inside there. So g of x equals square root of x minus 1. And then there's a minus 2 on the outside. No vertical stretches, no flips, no reflections, anything like that. Okay, 3 more questions. Number 18. Use a graphing calculator to graph x equals 3y squared minus 6. This is also out of 4-3. Identify the vertex and direction the parabola opens. Now, I stated at the time in this section, if you did these, you graphed these in IM2. You actually, maybe, I don't know, but they were in a section in the Big Ideas Math textbook. What we're doing more so is playing with radicals. We actually want to get y by itself so we can use the graphing calculator to actually do it. I have predictions for what this thing could be, and there are other ways that we could state this out loud that'll work out, but I need to solve for y. They want us to solve for y. So we're going to add 6 to both sides. I'll keep the 3y squared over here. We'll get x plus 6, and then we'll divide both sides by 3. Now, that's also the same as multiplying by 1/3, and I want to leave the 1/3 on the outside. This is not a requirement. This is not a requirement. This is for me to give you better predictive values of the answer without actually needing to do distribution. And then I got to take the square root of both sides. Now, this is where you'll be left with a plus or minus. This is where it actually becomes a full parabola. There are 2 equations we're going to write, and this is partly why we have to do this in the calculator this way. So plus or minus 1/3 times, or the square root of 1/3 times the quantity x plus 6. Now my predictions based on this, and they won't be wrong, my predictions on this are the vertex will be at -6, 0, and this will open to the right. The reason I think this is because if we think about how these things are graphed without it, when in parentheses like this is your true h value. The value of x that gets you 0 is -6. Right? If I distributed 1/3, then it would say plus 2, and 2 is not your h value. The 1/3 doesn't do anything with this information, except, well, sort of. It's positive, so it's going to open to the right, not the left. And the 1/3, though, means a horizontal stretch by a factor of 3. So it's going to be a graph that looks, here's -6, 0. It's going to be graphing kind of like that. It's going to do both of those. So let's go to the graphing calculator, the one that I reset. I'm going to write out the positive square root of 1/3 times x plus 6. That's got to be in parentheses. Or you can distribute the 1/3 x and make it 1/3 x plus 2 or anything like that. But anyway, you need a negative here on this one, and you got square root of 1/3 times, and here's x plus 6. And check this out. Start at -6, 0. It's going to go up and to the right, and it's going to go down and to the right. It'd be a full parabola like that. The vertex is at -6, 0. It opens to the right, and we are done. I'm going to copy and paste my graphing calculator version of this answer. I already wrote out the extra information that we needed. And that's good. See, don't those match up so perfectly? Oh, totally. Okay, number 19. It's a word problem. A jeweler is setting a stone cut in the shape of a regular octahedron. I thought it said rectangular octahedron. A regular octahedron is a solid with 8 equilateral triangles as faces as shown. Hopefully you can, maybe you can't see what that is, but it works. A formula for the volume of the stone is V equals 0.47 s cubed, where s is the side length in millimeters of an edge of the stone. The volume of the stone is 161 cubic millimeters. Find the length of an edge of the stone. They're not asking you to graph. This is section 4.1, so that wasn't graph-based. We are setting the volume equal to 161 and solving for s. So this requires two things: dividing by 0.47, and I can't imagine that that's a clean number. No reason to assume it is. We'll just leave it. We'll take the cube root of both sides. There's no plus or minus for two reasons. Number one, side length can't be negative. Number two, we're taking cube root, not square root. So our final answer will just be some cube root value. I mean, we're going to approximate it. I don't know what to round to. We'll just go to the calculator. See what makes most sense for what they're going to do with it. To cube root, we can raise it to the 1/3. Let's do that. 161 over 0.47 to the 1/3 power. Kind of like what we did on the previous problem that you see above. And this is 6.996. You're looking at 7, right? It's about 7 millimeters. Was this everything in millimeters at the time? I need to make sure. Yes, it was. So S is around 7 millimeters. I'll just say 7. That's clearly what they were going for. We'll leave it. And the last question is number 20. Pretty good time overall. An investigator can determine how fast a car is traveling just prior to an accident using the model S equals 4 times the square root of D. Doesn't that remind you? I can't remember what his occupation was, but if you see, I might be confusing two movies. I'm either thinking of Mission Impossible 3 or Fight Club, which one they talk about that stuff. It's one or the other, and I can't remember which. Anyway, it's not Mission Impossible 3. That's Traffic Patterns. I think it's Fight Club. Listen to what Edward Norton says when he describes his job to Brad Pitt. It might be something like this. Anyway, S equals 4 times the square root of D, where S is the speed in miles per hour of the car and D is the length in feet of the skid marks. Graph the model. Okay, I will, but I want to see the rest. The length of the skid marks of a car is 90 feet. Was the car traveling at the posted speed limit prior to the accident? Explain your reasoning. Okay, for this graph here, I'm trying to think of which graph thing I want to use. I think I'll still just use this one, so I'm providing the same graph paper as I used before. So I'm going to use this. 4 times the square root of D. Remember, S is your Y and D is your X here. This is a vertical stretch factor. So instead of over 1 up 1, it's going to be over 1 up 4. Instead of over 4 up 2, it's going to be over 4 up 8. 2 times 4. And instead of over 9 up 3, it's over 9 up 12. Now that technically doesn't fit here, but I'm going to force it. Here's 10, 11, 12. I'm going to force it up like that. Here's a square root graph like that. And as your distance increases, your speed increases by a little less over time. We don't have the distance of 90 feet on the graph, but that's the graph itself. We could use a graphing calculator, but I kind of want to do this a little more based off this. Now it says if your distance is 90 feet, were you traveling at the posted speed? Oh, prior to the accident. Oh, that makes a lot more sense. Yeah, I don't know if that was the exact Fight Club thing either. I don't know. Anyway, S sub 90 equals, I thought they said at the time of the accident, not prior to. Anyway, 4 times the square root of 90. I don't know. Let's see. 4 times the square root of 90 is 37.94 mph. So they're asking, was the car traveling at the posted speed limit? No. The car was traveling faster than the posted speed limit, 35 miles per hour. $350. Yeah, that wasn't it. All right, and that's it, and that's all. All right, guys, this didn't cover everything as a whole. Obviously, a lot of the things in the sections had a lot more to say with these, but this was a pretty good, quick go around. So that'll do it for this one. This is Mr. Robinson. Take care. Thank you so much for watching. 3 more sections to go in the chapter. Let's get ready for them.